Welcome to our comprehensive journey through metallurgy, tailored specifically for ICSE Class 10 students. Metallurgy is the science and technology of extracting metals from their ores and preparing them for practical use. In this video, we'll break down the entire process, from the basics of ores and minerals to the advanced techniques used in refining metals. Whether you're aiming to ace your exams or simply want to understand how everyday metals are produced, this series will guide you step by step. Let's begin by understanding what metallurgy really means and why it's so important in our daily lives. Before diving into metallurgy, it's crucial to distinguish between ores and minerals. Minerals are naturally occurring substances found in the Earth's crust, while ores are minerals that contain a high enough concentration of a metal to make extraction economically viable. For example, bauxite is an ore of aluminum, while hematite is an ore of iron. Understanding this difference helps us identify which rocks are valuable for metal extraction and which are not. This foundational knowledge sets the stage for all metallurgical processes that follow. Ores can be classified based on the type of metal they contain and the chemical composition. The main types include oxide ores, sulfide ores, carbonate ores, and halide ores. Each type requires a different extraction method. For instance, oxide ores like hematite are easier to reduce, while sulfide ores like galena need roasting. Recognizing the type of ore is the first step in determining the most efficient extraction technique. This classification is essential for understanding the subsequent steps in metallurgy. Metallurgical process involves several key steps: concentration of ore, extraction of metal, and refining. Concentration removes unwanted materials, extraction isolates the metal, and refining purifies it. Each step uses specific techniques depending on the type of ore and the desired metal. Understanding these steps provides a roadmap for how raw minerals are transformed into usable metals, which are then used in everything from construction to electronics. Concentration, also known as ore dressing, is the process of removing impurities like sand and clay from the ore. Common methods include gravity separation, magnetic separation, froth flotation, and leaching. The choice of method depends on the nature of the ore. For example, magnetic separation works well for magnetite, while froth flotation is ideal for sulfide ores. This step ensures that the ore is enriched and ready for the next phase of extraction. Gravity separation is one of the oldest methods used to concentrate ores. It relies on the difference in density between the ore and the impurities. The ore is crushed and washed with water, causing the heavier metal particles to settle at the bottom while lighter impurities are washed away. This method is especially effective for ores like gold and tin. It's simple, cost-effective, and environmentally friendly, making it a popular choice for certain types of ores. Magnetic separation is used when either the ore or the impurities are magnetic. The crushed ore is passed over a magnetic roller which attracts the magnetic particles and separates them from the non-magnetic ones. This technique is commonly used for ores like magnetite and chromite. It's a quick and efficient way to purify ores before further processing, ensuring that the metal extracted is of higher quality. Froth flotation is a method used mainly for sulfide ores. The powdered ore is mixed with water and special chemicals that make the metal particles hydrophobic. When air is bubbled through the mixture, the metal-rich froth rises to the surface and is skimmed off, leaving impurities behind. This technique is highly effective for ores like copper and zinc, ensuring a high concentration of metal for the next stage of extraction. Leaching is a chemical method used to extract metals from ores by dissolving them in a suitable solvent. For example, bauxite is leached with sodium hydroxide to extract aluminum. The solution is then processed to recover the metal. Leaching is especially useful for ores that are not amenable to physical separation methods. It's a vital technique in modern metallurgy, particularly for extracting metals like gold and aluminum. Once the ore is concentrated, the next step is to extract the metal. The extraction method depends on the reactivity of the metal. Highly reactive metals like sodium and potassium are extracted by electrolysis, while less reactive metals like iron are extracted by reduction with carbon. The choice of method ensures maximum yield and purity. Understanding these extraction techniques is crucial for mastering the fundamentals of metallurgy. Metals that are more reactive than carbon, such as potassium, sodium, calcium, magnesium, and aluminum, cannot be extracted by reduction with carbon. Instead, they are extracted by electrolysis of their molten salts. This process uses electricity to break down the compounds and release the pure metal. Electrolysis is energy-intensive but necessary for these highly reactive metals, ensuring their extraction is both efficient and effective. Metals that are less reactive than carbon, such as zinc, iron, and lead, can be extracted by reduction with carbon. In this process, the ore is heated with carbon, which removes the oxygen and leaves behind the pure metal. This method is widely used in the extraction of iron from its ore in blast furnaces. It's a cost-effective and practical approach for extracting these metals on a large scale. Some metals like gold and silver are even less reactive than hydrogen. These metals are found in their native state and do not require extraction from ores. They are simply separated from impurities by physical methods such as washing and melting. This is why gold and silver have been used by humans for thousands of years, as they are easy to obtain in pure form. Reduction by carbon is a key method for extracting metals like iron and zinc. The ore is mixed with coke, a form of carbon, and heated in a furnace. The carbon reacts with the oxygen in the ore, leaving behind the pure metal. This process is central to the production of iron in the steel industry and is a cornerstone of modern metallurgy. Electrolytic reduction is used for extracting highly reactive metals. The ore is melted and electricity is passed through it, causing the metal ions to migrate to the cathode and get deposited as pure metal. This method is used for metals like aluminum and sodium. Although it requires a lot of energy, it's the only way to extract these metals efficiently from their ores. Thermal decomposition is a process where heat is used to break down compounds into simpler substances. For example, mercury Roman II oxide decomposes on heating to give mercury and oxygen. This method is suitable for extracting metals that decompose easily when heated. It's a straightforward process, often used in laboratory settings to demonstrate the principles of metallurgy. After extraction, metals often contain impurities that must be removed to obtain pure metal. Refining is the process of purifying the extracted metal. Common methods include electrolytic refining, distillation, and zone refining. Each method is chosen based on the metal's properties and the type of impurities present. Refining ensures that the metal is suitable for industrial and commercial use. Electrolytic refining is a widely used method for purifying metals like copper and silver. The impure metal is made the anode, and a thin sheet of pure metal is the cathode. When electricity is passed through the electrolyte, pure metal deposits on the cathode while impurities fall off as anode mud. This method produces metals of extremely high purity, essential for electrical and electronic applications. Distillation is used to refine metals with low boiling points, such as zinc and mercury. The impure metal is heated until it vaporizes, and the vapor is then condensed to obtain pure metal. This method effectively separates the metal from impurities that have higher boiling points. Distillation is especially useful for metals that are volatile at relatively low temperatures. Zone refining is a technique used to obtain ultrapure metals, especially semiconductors like silicon and germanium. A rod of impure metal is passed through a heating coil which melts a small region. As the molten zone moves, impurities concentrate at one end, leaving behind pure metal. This method is crucial for producing materials used in electronics and computer chips. Alloys are mixtures of two or more metals or a metal and a nonmetal designed to have improved properties. Common examples include steel, iron, and carbon, brass, copper, and zinc, and bronze, copper, and tin. Alloys are stronger, more durable, and often more resistant to corrosion than pure metals. They play a vital role in construction, transportation, and manufacturing industries. Alloys are engineered to have specific properties such as increased strength, hardness, resistance to corrosion, and better electrical conductivity. For example, stainless steel is resistant to rust, while solder an alloy of tin and lead has a low melting point, making it ideal for joining metals. The unique properties of alloys make them indispensable in modern technology and infrastructure. Let's look at some common alloys and their uses. Steel is used in construction and machinery, brass in musical instruments and fittings, and bronze in statues and metals. Each alloy is chosen for its specific properties, ensuring the best performance in its application. Understanding the uses of alloys helps us appreciate their importance in everyday life. Corrosion is the gradual destruction of metals by chemical reactions with their environment, such as rusting of iron. It leads to loss of strength and appearance, causing significant economic losses. Understanding corrosion is essential for developing methods to protect metals and extend their lifespan, especially in construction and transportation. There are several ways to prevent corrosion, including painting, galvanizing, alloying, and using protective coatings. Galvanizing involves coating iron with a layer of zinc, which prevents rusting. Regular maintenance and the use of corrosion-resistant alloys also help protect metals from environmental damage, ensuring their longevity and reliability. Metallurgical processes can have significant environmental impacts, including air and water pollution, habitat destruction, and resource depletion. It's important to adopt sustainable practices, such as recycling metals, using cleaner technologies, and minimizing waste. Responsible metallurgy ensures that we meet our needs without compromising the environment for future generations. Recycling is a key aspect of sustainable metallurgy. Metals like aluminum and steel can be recycled repeatedly without losing quality. Recycling saves energy, reduces pollution, and conserves natural resources. It also helps lower production costs and supports a circular economy, making it a win-win for both industry and the environment. Metals and alloys are everywhere in our daily lives, from the utensils we use to the vehicles we drive and the buildings we live in. Understanding metallurgy helps us appreciate the science behind these materials and the processes that make modern life possible. It also highlights the importance of responsible use and recycling. Metallurgical industries are vital to the economy, providing materials for construction, transportation, electronics, and more. These industries employ millions of people worldwide and drive technological innovation. Understanding the basics of metallurgy opens up career opportunities in engineering, research, and manufacturing. Safety is a top priority in metallurgical processes. Handling high temperatures, chemicals, and heavy machinery requires strict safety protocols. Workers must wear protective gear and follow guidelines to prevent accidents. Ensuring safety not only protects workers but also improves efficiency and product quality in metallurgical industries. Metallurgy has a rich history dating back thousands of years. Early humans discovered metals like copper and gold in their native state and learned to extract and shape them. The discovery of bronze and iron revolutionized societies, leading to the Bronze Age and Iron Age. Studying historical metallurgy gives us insight into human progress and technological development. Modern metallurgy combines traditional knowledge with advanced technology. Techniques like computer modeling, automation, and nanotechnology have transformed the field. Today, metallurgists develop new alloys, improve extraction methods, and create materials with unique properties for specialized applications. The future of metallurgy is bright, with ongoing research and innovation. Various equipment is used in metallurgy, including furnaces, crushers, separators, and electrolytic cells. Each piece of equipment serves a specific purpose, from crushing ores to refining metals. Understanding the function and operation of these tools is essential for anyone interested in metallurgical engineering or industrial processes. Chemistry plays a central role in metallurgy. Chemical reactions are involved in every step, from concentration to extraction and refining. Understanding oxidation, reduction, and electrochemical processes is crucial for mastering metallurgy. This knowledge helps in developing new methods and improving existing ones for better efficiency and sustainability. Physics is also important in metallurgy, especially in understanding properties like conductivity, malleability, and ductility. Physical principles guide the design of equipment and processes, ensuring optimal performance. Knowledge of physics helps metallurgists develop materials with desired mechanical and electrical properties for various applications. Metals and alloys are essential in electronics, forming the backbone of circuits, wires, and components. Copper, aluminum, and gold are widely used for their excellent conductivity. Metallurgy ensures these metals are pure and reliable, supporting the rapid growth of the electronics industry and modern technology. Metals like titanium and stainless steel are used in medical implants, surgical instruments, and diagnostic equipment. Their strength, biocompatibility, and resistance to corrosion make them ideal for healthcare applications. Metallurgical advances continue to improve the quality and safety of medical devices, enhancing patient care. The transportation industry relies heavily on metals and alloys for vehicles, aircraft, ships, and trains. Lightweight alloys like aluminum reduce fuel consumption, while strong steels ensure safety and durability. Metallurgy enables the development of advanced materials that meet the demanding requirements of modern transportation. Metals like steel and aluminum are fundamental to construction, providing strength and flexibility for buildings, bridges, and infrastructure. Alloys are chosen for their specific properties, ensuring structures are safe, durable, and cost-effective. Metallurgy continues to drive innovation in construction materials and techniques. Metals have been used in art for centuries, from sculptures and jewelry to decorative objects. The unique properties of metals allow artists to create intricate and lasting works. Metallurgy provides the knowledge and techniques needed to shape, join, and finish metals for artistic expression. The future of metallurgy is exciting, with ongoing research into new materials, sustainable processes, and advanced technologies. Innovations like 3D printing with metals, smart materials, and green metallurgy are shaping the industry. Staying informed about these trends is essential for students and professionals alike. Let's review some key terms: ore, mineral, alloy, reduction, electrolysis, refining, corrosion, and galvanizing. Understanding these terms is fundamental for mastering metallurgy and performing well in exams. They form the building blocks of all metallurgical concepts and processes. To help you prepare for your ICSE Class 10 exams, let's look at some sample questions. For example, define metallurgy. What is the difference between an ore and a mineral? Explain the process of froth flotation. These questions test your understanding of key concepts and help reinforce your learning. Success in metallurgy exams comes from understanding concepts, practicing diagrams, and solving past papers. Focus on key processes, memorize important terms, and practice writing clear, concise answers. With consistent effort and the right approach, you'll be well prepared to excel in your ICSE Class 10 metallurgy exam. You've covered the essentials of metallurgy for ICSE Class 10, from the basics of ores and extraction to refining, alloys, and applications. Remember, metallurgy is not just about memorizing facts, it's about understanding the processes that shape our world. Keep exploring, stay curious, and apply your knowledge to real-life situations. Good luck with your studies.